And Jen, would you like the honors of starting off the presentation?
Sure. Can everybody hear me okay?
I can hear you well.
All right, great. So thanks for giving us an opportunity to come and share some of the new things that we're working on with reservoir sedimentation at Reclamation. We really wanted to try and cover some of the reframing that we're doing at Reclamation to create a new conversation about how do we maintain these really important reservoir assets, particularly when they are losing storage every year due to sedimentation, which is a really tough long-term problem. So we'll start out with some of the things we're working on that communication story with our resource managers and leadership. We'll talk a little bit about our detection and monitoring strategies that we've been putting into place, some new research and numerical modeling that you may be interested in, some of our reservoir sediment management strategies, and then we're going to talk about some of the challenges at Reclamation and how we're doing a prize competition to crowdsource some ideas, because we can use all the help we can get. You're looking at a picture there in the top right of Peonia Reservoir in Colorado, which is one of our sites and facilities that has some pretty severe sedimentation at the intake that's shown there in the pop-out photo.
So Reclamation has 294 storage reservoirs. We have other dams that are just for diversion of water, but 294 storage reservoirs with 141 million acre feet of storage capacity. And these reservoirs are considered assets that need to be managed over the long term, but the dam outlets were originally designed to function over the sediment design life or until the dead storage was full of sediment. And so once the outlet becomes buried, it may function for a while, maybe a few decades, but then at some point it may get plugged out. And this lower graph here, you can see where these dams are located, and there's Glen Canyon Dam on the Colorado River. So this graph shows a reservoir in 4 stages. This illustration was created by Greg Morris, but here we've got the riverbed sloping downstream. We've got a dam here, brand new, and you can see they don't put the outlet right on the bottom. Usually put it up some distance, and all the storage below here is called the dead storage. Everything above here is live storage or beneficial storage. And then after some initial period of operation, you start to see sedimentation. So you get delta sediments or coarse sediments here, sand and gravel typically, that will form a delta and deposit up near the normal water surface of the reservoir. And these deltas can extend quite a ways upstream depending on the slope of the river. For something like the Missouri, it can go tens of miles upstream. And then you have the finer sediments going past the delta, depositing here along the lake bottom. So in this sketch, everything's going according to plan. And then you get to diminishing beneficial storage, where the dead storage pool is now full. Sediment's actually higher than the outlet. This delta is advancing downstream. And then you get into severe sedimentation impacts if it goes long enough. And usually high hazard dams in this setting are going to be removed, some sort of decommissioning. So sedimentation is reducing the storage capacity over time and may eventually impair the dam and reservoir facilities. And sedimentation impacts will occur long before the reservoir completely fills with sediment. And severe droughts will lower the reservoir pools and allow sediment to move closer to the dam, also stress vegetation in the upstream watershed, and sometimes leading to wildfire, and that's going to increase future sediment yields or loads to the reservoir. So Reclamation is implementing a reservoir sedimentation monitoring policy to better track the sedimentation impacts using things like aerial LiDAR to scan the topography above water, and then bathymetric surveys by boats global positioning system and multi-beam depth sounders. So instead of one depth sounder below the boat, it's got hundreds of depth sounders working simultaneously to scan the reservoir bottom. And then we can put that into detailed maps. And then as far as communicating this reservoir sedimentation paradigm, we've done several things. We've had white papers that are available on the web for free. We've had international workshops. Dr. Paul Boyd has been quite involved in those as well. We did them in 2018, in August in 2021. We've also been putting on journal articles. We've got a couple out there now and more on the way. And then over the period 2018 and 19, we've presented and recorded 7 webinars, and they're available for free on the web to anybody that wants them. And then for our detection and monitoring, we have a proposal to form an agency-wide reservoir sediment survey team. And we're using advanced technology, the survey grade GPS, so we can get accuracy within centimeters of our position, these multi-beam depth sounders, advanced data processing software, and partnering with the Army Corps using a compressed high intensity radar pulse, which is known as CHIRP. That it's a type of sonar that you can try to get an idea of sediment thicknesses. And that can be quite valuable where you don't have pre-dam surveys. And then we've recently developed new guidelines for developing reservoir sedimentation monitoring plans, and that's available on the web for free as well. And Jen, I'll turn this one over to you if you would like.
Sure. Dr. Melissa Foster and Rob Hilldale and our groups have been working on some tools to help us better predict sedimentation in our reservoirs and how we can really do more decadal outlooks into the future to see if we're going to be able to maintain our storage asset, or if not, how fast and when that might occur at our different facilities based on geographic location, watershed conditions, size of the reservoir, how they're operated, all those different factors. And one of the most important information pieces for us to help understand those trends, even with our predictive tools that actually go out and do those sedimentation surveys. And surprisingly, at Reclamation, we've only done about 40% of our facilities. So part of our messaging is really trying to develop really cost-efficient tools and letting our resource planners know how much different reservoir surveys would cost. So we're developing a new tool that'll be on a dashboard, and we have a manual out on our website that gives folks an idea. You know, we're talking tens of thousands or something greater, depending on the size of how much actually cost to do these sedimentation surveys. So we can build that into a bigger planning effort and help prioritize and get these accomplished. Another really cool effort that we're working on is a dashboard that our resource managers can look to see where they've done the surveys and what capacity has been impacted by sediment in the reservoirs. So this is a tool that'll be based in ArcGIS, and we'll be using both those sedimentation surveys, and then we also help to build in some of the other predictive tools, either in concert with the sedimentation surveys or where we don't have a survey yet, to try and see how much sediment might be affecting those areas. So one of the really cool tools that's being developed by Dr. Foster is looking at how the upstream basins may be affecting reservoir sedimentation predictions in the different sites. There is also a colleague doing it at St. Louis University for the Corps of Engineers facilities. So this is pretty cool. They look at how big the basin is upstream of the dam, but then also of that basin, how many locations have facilities, other dams that could have significant sediment storage that Tim is pointing to there. So by not only just looking at the total basin above the dam and then kind of subtracting if there is storage and sedimentation storage opportunities upstream, we can see kind of what the real prediction might be cumulatively throughout the watershed. And it's pretty significant. There's 30,000 upstream dams in the analysis she's doing. So it's a really large factor. And then the idea is to be able to predict some capacity loss, and just showing an example here, say in 2050, where are the sites that have the biggest predicted loss based on this type of analysis? What sites may be operating slower, so that we can start to focus our efforts and priorities where the sediment health cards are worse. All right, I'll shift it back to you, Tim, for this one.
Sure. And so in terms of our research and numerical modeling, Dr. Young Lai of our group has developed SRH 3D. It's a computer model developed to simulate sediment turbidity currents, and has been applied to a reservoir in Taiwan. And here's just an example from his journal article. And this may not look super exciting, but this is a laboratory experiment where they're putting a plume of sediment in and it's beginning to disperse. So this is after just a couple of seconds, and after 14 seconds and 26 seconds and 38 seconds, it's just dispersing or transporting through this fluid here. And then what you're seeing here is the numerical simulation of that. And so they're actually matching pretty darn well. This is not an easy thing to simulate in a 3D model, but Young has been able to successfully do that. We're also developing a new computer model to simulate the economics of reservoir sedimentation. And this is one example where a reservoir we're calling Muddy Reservoir. We have the initial, so these are years in from when the dam is first put into service. And then these numbers are the negative numbers are the costs, and the numbers up here are the benefits. And so there's the original planning, design, and construction cost acquisition, and then you start getting a stream of benefits. There are some O&M costs, and then you eventually get to decommissioning. And then there are some restoration benefits after decommissioning, but the reservoir benefits have ended. And so that's this example. And then if the reservoir were managed sustainably, then those benefits continue indefinitely. And so economics is comprehensively considering all the benefits and costs to society. So it doesn't really matter who's benefiting or who's getting the cost. It just considers all those and how they change over time. When they occur is actually quite important to economics. And the benefits and costs do change with reservoir sedimentation. And over time, sedimentation can lead to diminished reservoir storage and recreation benefits, upstream impacts to lands, infrastructure, and habitat, and downstream costs to lands, infrastructure, and habitat, and then eventual dam decommissioning. And so sometimes people think that doing nothing is the cheapest option, but when you actually look at all the costs and benefits and how they're changing over time, sometimes you get a different conclusion that maybe managing the sediment is actually more economical to society than just ignoring the problem. Other research that we're working on is predicting reservoir drawdown flushing to improve reservoir sustainability, and also quantifying the development and dynamics of reservoir delta riparian habitats. Some of our reservoir deltas, like on Elephant Butte Reservoir in the Rio Grande, have pretty extensive stands of woody vegetation that endangered birds are utilizing. And so we're trying to understand that. Also investigating the physical processes impacting fish passage on reservoir deltas and potential solutions. In some cases, the reservoir may drop down and then low flows are flowing across the delta surface, but then they go subsurface and then fish can't really pass on dry channels, right? And so they can't go from the reservoir up the delta tributary channels until the reservoir pool gets full again. And then looking at sediment management strategies, we put them into categories of reducing the sediment yield from upstream. Here's an example from Japan where they've using a concrete lattice to stabilize a landslide. Or here also in Japan, they've constructed a check dam to trap sand and gravel upstream. Those have to be cleaned out. Other categories are routing the sediments either through or around the reservoir. Here's an example from also in Japan where they drilled a tunnel and sent the sediments around this way. And then you can also remove the sediments either by, let's see, you can also draw the reservoir down and try and flush the sediment or sluice the sediments on through, or for sediments that have already deposited, you might try to lower the reservoir and flush those sediments through. And then also either mechanical or hydraulic dredging. And then there's also adaptive strategies that try to cope with the sediment that's coming in. And Greg Morris put together this nice chart. It's got a lot of detail to it, but it's the same idea as you take the reduced sediment yield from upstream, looking at reducing that production in the watershed, sediment trapping perhaps, soil erosion control, revegetation, channel erosion control, looking at forest, rangelands, farms, construction sites and developed areas, trying to minimize erosion there. There's also dispersed structures, check dams, farm ponds, gully stabilization, stream channel stabilization and restoration. And then for routing the sediments, there's this bypass option where you have a flood bypass channel or a bypass tunnel. Or sometimes you have off-stream reservoirs where you try to divert the water and not the sediment into the reservoir. And then there's the sediment pass-through. You draw the reservoir down and sluice the sediment. Or sometimes you get turbidity currents, and I have a slide on that a bit later, where you try to take these really high concentration sediment plumes and just send them right through the reservoir. And then for sediment that's already deposited, either remove or redistribute those sediments, either through mechanical excavation, dry excavation, or dredging, or hydraulic dredging. There's hydrosuction, airlift dredges, mechanical lift, agitation dredges, where you might modify operating rules, lowering the reservoir water surface, introducing hydraulic scour. There could be pressure flushing or trying to empty the reservoir and flushing it that way. And then river flushing below the dam, discharging the sediments below the dam or off channel. And then for adaptive strategies, looking at reallocating the storage. You're just going to have to accept the sediments are coming in, but you're trying to cope with it. You could modify the intakes, maybe raise the outlet works elevation so they can continue to function. You could raise the dam to increase the volume, or water loss and control conservation, and eventually decommission the dam. And then monitoring is, of course, required for all those options. So here was this example from Japan Miwa Reservoir, where in Japan, they've, like in Taiwan, they've got very high rapid rates of uplift. They've got earthquakes shaking things loose, and they've got typhoons washing all that sediment down to the sea. And so they've really run out of room for reservoirs. It's not like they can just keep building new dams. So they're doing really a full court press on sediment management, like they are doing in Taiwan. And here they've drilled a 7-meter diameter tunnel, the entire length of the reservoir. They have a diversion dam upstream. They have a device that continuously measures the concentration of the inflowing sediments. And when that concentration gets high enough, they open up the gates to the tunnel and sediment comes through here and out here below the dam. Sometimes you get reservoirs with really high concentrations coming in. A lot of times in the arid Southwest, where we call them turbid density currents, where you have this maybe 10,000 parts per million coming in. That sediment-laden water is actually heavier than the reservoir water, and so it dives and flows along the reservoir bottom all the way to the dam. And this can go on for tens of miles, depending on the right site conditions. And if there is a low-level outlet in the dam and it's open, then you can vent this turbidity current right on through the dam. They're doing some of these in Taiwan. And then there's pressure flushing. This is an example from one of Paul Boyd's projects, Cherry Creek Reservoir near Denver, or in Denver actually. And here they're just opening up the outlet for a while and flushing the sediment from right around the outlet works. Doesn't really remove any high volumes of reservoir sediment, but it does remove the sediment around the outlet works. And then a lot of downstream monitoring was done as part of that. That gets done, I think, every May. And here's another example from one of Paul Boyd's projects, Spencer Dam, which has since failed, but that reservoir was basically full of sediment, and then lowering the reservoir pool down and flushing that sediment on down to the downstream river channel. So if you can afford the water, this technique can work well. You get very high concentrations downstream, and so that could have some severe impacts to the aquatic environment, depending on what's down there. And then remove or redistribute the sediments either through mechanical or hydraulic dredging or dry excavation. In a lot of parts of the arid west, you really can't use a lot of reservoir water for sluicing or bypassing floods or drawing down the reservoir. And so dredging uses some water, but a very small amount compared to all the other schemes. And so I think dredging actually may have a lot of promise for a lot of reservoirs in the West. And the idea would be to transport sediments. You could do it by barge perhaps, but we found that slurry pipelines are usually the least expensive option. But truck, conveyor belt, and for discharge to the downstream river channel, other beneficial uses, or if it's contaminated, maybe to a disposal site. And some of these beneficial uses could be soil augmentation for agriculture, land development, construction fill, concrete aggregate, wetland or other shallow water habitat creation, and shoreline beach development or augmentation, and of course to offset the downstream channel incision that may occur from trapping the coarse sediments in the reservoir. And there are a number of resources available. There are more all the time. I just have a small sampling here. George Annandale wrote Quenching the Thirst. That's a very good book. Reservoir Sedimentation Handbook by Craig Morris and Dr. Fan. These other publications dealing with reservoir sedimentation. Roland Hotchkiss at BYU, I think, had a hand in managing sediment in Utah reservoirs. And other publications, Sustainable Sediment Management in Reservoirs and Regulated Rivers. And this is experience from 5 continents. So just a small sampling, but there are many things out there. And we'll talk about some case studies within reclamation. This is one from McPhee Reservoir in Colorado. It's located on the Dolores River, is 10 miles north of Cortez. So it's in the southwest corner of Colorado. And drought triggered, big reservoir drawdown. And then they had to do reservoir dredging to remove sediment that blocked delivery to the water irrigation canals during the reservoir's lowest levels. When the reservoir was higher, that wasn't an issue, but with the reservoir that low, they had to do some dredging. So that reservoir had 4,470 surface acres, and they dredged about 13,000 cubic yards in that project. Pretty small dredging effort. And then there's Paonia Reservoir. It was constructed on Muddy Creek. And of course, they were expecting a lot of sediment. Most reclamation and Army Corps reservoirs have 100-year sediment design lives. This one just had a 50-year. And that reservoir had 315 surface acres, and it accumulated 8.75 million cubic yards. And, a lot of times wood flows into reservoirs. Some of it stays floating and some of it sinks. And when it sinks into the dead storage, kind of nobody knows and nobody cares. But when that dead storage is full of sediment, now when that wood sinks to the bottom, it can go around the outlet to the dam. And so here they were expecting a lot of sediment, so they put the outlet works 70 feet above the reservoir bottom. There's a person for scale. It was built in 1961. And then 50 years later, that 70-foot high outlet tower was buried in sediment and all that wood. And they had to use a long reach excavator to try and remove some of that wood and sediment from around the outlet. Kind of like building a beaver dam around your outlet works.
Yeah, and their sediment management plan for Paonia, after doing some of the emergency excavation of this sediment at the intake, they do continue to have manual removal of the wood around the intake, and they're planning on trying to use basically sluicing in the spring when they have higher flows to try and maintain their current capacity to keep operations flowing at this time.
Yeah, and their sluicing strategy, this reservoir is actually pretty small to the watershed. They can fill this reservoir 5 times in a year if they wanted to. So emptying the reservoir is not a huge issue, but at the beginning of the irrigation season, they want to have the reservoir as full as possible. And so what the strategy is, as Jen was saying, was just keep the reservoir low because it got emptied from the previous irrigation season, and allow those inflowing sediments to pass on through hopefully without plugging the outlet. And then fill the reservoir near the end of the spring snowmelt. So they've got to watch the hydrology and make sure they still have enough water to refill the reservoir. But they're losing capacity. They've lost about 25% of their storage capacity, and the sediment design life is gone. So it's a tough problem. And I'll let you take on these, Jen.
Sure. So another case study where Reclamation is experiencing a lot of sedimentation is Imperial Reservoir, which is near the border of Arizona and California. It's on the Colorado River, close to Yuma. It's got about 69 surface acres, and that entire area, it has to be dredged. This is not a storage reservoir, but it is used to continually divert water for irrigation into canals. And so they basically 24/7, 365 days a year have to dredge. They have their own dredging equipment on site. And then they have sediment storage ponds where they try and capture the sediment, although some of it gets flushed through the system. They had some emergency dredging near the outlet works using a Corps of Engineers, kind of a military exercise, if you can believe it. And it was really challenging because they had so much wood and it was a really difficult area to access. And they have almost 2 million cubic yards of sediment at the site, and it is continuing, not looking to slow down anytime soon. And then Horseshoe Reservoir is another facility on the Verde River that has 74 million cubic yards of sediment. So it has a severe sedimentation problem. It's virtually lost most of the operational capacity from previous. And so they're trying to maintain what they have left and think about how to increase it to continue operations into the future. So they haven't come up with a sediment management solution here, but one thing that they are considering is enlarging the next downstream dam called Bartlett Dam to increase storage to continue operations. So Tim's showing there a picture of the existing dam facility and kind of a mock-up of what the modified larger Bartlett Dam would look like. And you can see that the new dam would also then extend farther onto the landscape beyond the footprint of the current one. And this is a really challenging study because either way, even if they can increase the storage downstream, they're still going to have to deal with the upstream sedimentation in Horseshoe and think about how that might be passed and managed in Bartlett. So it's very difficult and kind of in the works of looking at different alternatives now.
So another case study is the Glen Canyon Dam, which is upstream of the Grand Canyon. And all that Lake Powell traps all the sediment, of course. So Grand Canyon is not getting as much sediment as it naturally would. So there were some folks interested in sediment augmentation of the Grand Canyon. And Lake Powell is we concluded the best source. But the idea would be to seasonally increase turbidity, provide cover for native fish. This is the endangered humpback chub, but that fish and other native fish evolved in very turbid environments. So they're used to the sediment loads. And today, unless the tributaries have rainstorms, the river is quite clear and the native fish will not come out in the daytime. They hide deep in the daytime and only come out at night. Unless the tributary storms are producing turbidity in the Colorado River, then they'll come out in the daytime. So the idea would be to add more silt and clay to the river to increase that turbidity. And then also annually increase sandbars or sand supply to build larger sandbars in conjunction with beach building flows. These beach building flows are these very short duration but high releases from the dam to mobilize sediment stored in eddies and in pools and interstitial spaces on the bed of the Colorado River, and then have them deposit as these sandbars. So this is Glen Canyon Dam is right here. This is all of Lake Powell. The dam is in Arizona, but most of the reservoir is in Utah. This is San Juan Canyon, or excuse me, Navajo Canyon. That's just one of the many tributaries of Lake Powell. But the idea was to use the sediment in this canyon. They appear to be fairly clean, and construct a floating pipeline, go overland here, and either put it right below the dam or take it on downstream to Lee's Ferry, and not increase sediment in this 16-mile reach, which is kind of a prized blue ribbon trout fishery. And one thing we looked at was there's a lot of recreation on Lake Powell. So if you have a floating pipeline and boats can't cross, that's going to be a huge problem. So we came up with a scheme where you would have anchors that would just rest on the sediment. So rather than disturbing archaeological sites that might be inundated by the reservoir, putting these anchors on just the sediment shouldn't harm anything. And then having a series of buoys that would suspend this pipeline. So the pipeline would be maybe 15 feet below the water surface. And there was actually going to be 6 pipes, 3 for sand and 3 for silt and clay. And then there would be a pulley and counterweight system. So as the reservoir went up and down, the pipeline would still be anchored. So it could handle the reservoir fluctuations. And then boats could pass between the buoys and cross over the pipeline.
All right, so Tim gave a really nice overview of some of our case studies and existing sediment management techniques, but we're open to any ideas, and one way that we can do that with our current authority in the federal government is to throw out a prize challenge. And prize challenges are very unique in that we're basically crowdsourcing ideas across the world to see if there are other solutions in other countries, maybe in other industries that can cross-pollinate into our questions and concerns to help us do a better job maintaining our reservoirs. And because sediment management, particularly typical dredging, can be very expensive, we're really looking to crowdsource ideas that can help reduce that cost and make it more affordable. So this competition, you can find information about it. This will be kind of our last part of our presentation here. It's on the HeroX website. So it's sponsored by the Corps of Engineers and Bureau of Reclamation. And then we have 3 contractors that help us run the competition. So it actually is hosted through NASA's Tournament Lab, which was kind of interesting to me to get involved. So we're not going to space, but we are trying to save our reservoirs, and NASA has a tournament lab that helps us run these competitions. HeroX is our vendor that facilitates the competition. And then what's really cool is the teams get to work with this organization called FedTech to not only work on the technical part, but FedTech helps them develop their business model and really engage in the industry. So the goal of the competition is to develop and demonstrate innovative approaches that have some kind of efficiency or capability beyond the existing sediment removal. So if you think of developing a new technology or idea, maybe you're just sitting at a restaurant, it's on the back of a napkin, and that's your one, and if you get all the way to 10, you're out and it's in the industry and you're working on it. So we're trying to help them move along that development scale in this competition. And the goal is, well, it may be very difficult to recover lost storage. We want to at least be able to annually move sediment that's coming in kind of through the system to try and maintain what we have. And if any of those solutions can do even better, that's even more fantastic. So some of the current methods we've been talking about, those dredging can be pretty expensive in a lot of cases, depending on the access and how far the sediment has to be moved to that beneficial reuse. It can be $20 a cubic yard or even more. We do find the cheaper implementation is where you can do a local storage or beneficial reuse. The farther you have to take that sediment, or the deeper and farther up the reservoir you have to get that sediment, it just really elevates the cost. The durability is really a problem. We have a reservoir here near Denver called Staunches Springs, and it was really problematic when they tried to dredge it from wildfires, because the sand and gravels were just really causing so much abrasion in the pumping and delivery system to reroute those sediments out of the reservoir. So anything that can really help reduce downtime and failures and deal with that abrasion would be a big improvement. And then versatility, especially a lot of our big reservoirs in the West. We're dealing with lots of storage fluctuations. They can be all different sizes, really deep depths. So it's not the standard dredging applications. So we're trying to figure out ways that can really be used and incorporated in those big scale facilities. And then, as Tim mentioned, it's very difficult, especially right now in our mega drought, to really lose any water through flushing or sluicing. So ideally, we'd like these solutions to be able to incorporate kind of in the operating scenarios without having to reduce and use a lot of the water. So we did give the teams that were competing some constraints. So we didn't want to have significant drawdown in order for their solutions to be effective, again, to save the water. We recognize that, we've got coexisting recreational activities, marinas, boaters, paddle boarders now, all kinds of recreation. So we really don't want to endanger any visitors while they're operating. So they have to be able to kind of, operate within that environment. And we don't want them to have any harmful materials, of course, to, support the ecosystem and not endanger our wildlife. So the way we set up the competition, it's been going for a while. It has over $500,000 in prize money for the teams, which is pretty cool. So we're currently in phase 3. The first phase 1 was proposals of the idea and concept of how they would improve reservoir sediment removal. So 5 teams competed and won in that phase, and they each got $75,000 to go into phase 2. And then we recently this spring completed phase 2, and the top 3 teams won an additional $25,000. And they demonstrated to a panel of judges in industry, kind of their ideas and how they were moving along. And now we're in the final phase 3. So in August, the 3 top teams will submit. They're going to be showing not only their idea, but a prototype and a demonstration. So it's been really excited to see all the progress that the 3 teams have made. They've been receiving support, not only technically, but their business plan development, polishing their elevator speech story. And then the top team that gets selected in August will win $100,000. And I'll have a couple slides here that just gives a real highlight. But in September, we're going to have a final presentation for all 3 teams where everyone can get to see their ideas. So 3D Dredger is one of our top 3 teams. So Nicholas LeBry and Kenneth LeBry, kind of a father-son team. They're really cool. And they've been working on this autonomous dredging system to handle sediment and different debris. So they have 3 different attachments on their removal system, which is pretty cool. So they can deal with different types of sediment or wood and kind of switch that out. And you can actually have it kind of set up and housed at the reservoir facility and be operating continuously. Sediment is Dr. Michael Dredging is the lead there, and some of his colleagues out of Germany. And they've been looking at this setting mover technology, so an autonomous vessel. So their idea on saving costs is to have it more independently operated without a lot of humans having to be on the operation and monitoring that full time. So they're looking at a solution that's really scalable, which is super cool. And their approach involves ideally passing the sediment downstream of the dam, but it could be routed to a different retention pond or other beneficial use. So it's been pretty cool to see how they're developing that. And then finally, our last team, MSAC International, is Dr. Baha Abulnaga, and he's out of Washington. So he's been kind of creating different parts of the system. One of it is through our prize competition with the slurry piston pump engine to try and get fine sediments out of the lake bed. And the other piece is funded through a National Science Foundation grant, which is really cool. And so he's been doing research on like capsules, like you would have with a bank teller, you know, with your money going up the capsule, that where you put like the gravels and sands in this capsule and like shoot it along to reduce abrasion issues. So it's really looking at how to move that sediment and take it out without a lot of water use. So that's kind of our 3 prize teams. And as I said, they'll be judged in August, and we're really hoping that they can insert themselves into the industry and have a chance to demo in a real case study. And we'll be having a showcase in September that we'll certainly share with this group. So that's it for our presentation today. So I hope everyone was able to hear and stick with us.
Thank you very much. One question that we always have with dredging or whatever method of removal for the sediment, is there uses for that sediment that they've developed in the Far East or in the Western states? Well, that's what we have. We're kind of a rural area. We don't have a big city that could use all the aggregate. Are there methods that people have been using to use that sediment that make it more cost effective?
Well, usually the cheapest beneficial use is downstream of the dam, because the reservoir is trapping all that sediment. And then when you release that clear water downstream, it's quite erosive. It takes a fair bit of, I mean, all rivers transport sediment, and it takes a fair bit of energy to move that sediment. So when you take the sediment out of the water and send the water downstream, now you've got water that's got a lot of extra energy. And so it starts eroding the stream bed and stream banks. And so putting the sediment downstream could offset that. Now the next reservoir downstream may have to deal with it, but you know, if you do that all the way down, you could really minimize a lot of coastal erosion. That's what they're doing in Japan, is sending it through whole systems of reservoirs that way to try and offset some of the beach erosion that's been going on at the coastal areas.
Yeah, and the next approach to that is pushing it downstream, but in a more like controlled and designed manner. But then that elevates the cost quite a bit. So using it certain sizes, but then that requires, you know, sieving through the sediment. Say if you want certain gravels or sands, depending on the habitat requirements downstream. It can be also used to try and mitigate where erosion is happening, to create bars or islands to create barriers to that hydraulic energy to retrieve it. And as you mentioned or alluded to, you know, we are trying to look at maybe reuse in industry, but, you know, if you don't have enough need for perhaps using it for concrete or landscaping or other things, you know, then you do have to travel that sediment. So that does elevate the cost, but we would like to look into areas that and potentially some of the lake bed or finer sediments. A lot of our agricultural areas are having a lot of soil loss, which so it could be beneficial to look into repurposing it for those uses too.
And the Army Corps has been conducting a whole research program on other beneficial uses of sediment. I don't know, Paul, if you want to say anything more about that.
Oh no, Paul, you sound kind of underwater or something. I think your sound audio is.
The audio is terrible. That's too bad.
Paul, your sound is not working. Bad radio connection. Maybe he can come back and answer the question if he has a clean connect.
That was unfortunate, but
You were saying something about limiting the channelization or at the rivers, but isn't there also a benefit for like down in New Orleans for building the delta or rebuilding it to help for protection rather than worrying about cutting away the beaches at the discharge?
yeah, those coastal deltas, I mean, the sediment thicknesses on some of the coastal deltas are thousands of feet thick, and they actually start to deform the Earth's crust a little bit. And so they settle over time. And so if you don't have any incoming sediments, then they just start sinking. And so then if you get sea level rise on top of that, it's a huge problem. So allowing the sediments to get down in the coastal area would have a lot of benefits.
Yeah, one of the projects we worked on that was a little unusual was the Eldan Dam removal up in northwestern Washington state, where 100 years of sedimentation in the reservoirs had really depleted the coastal area there in the Strait of Juan de Fuca. And that plan was to actually move the dams to release all the sediment. But if the dams have been left in place and just all the sediment routed, it's kind of the same concept. And the beach that has grown in the coastal area has completely changed the ecosystem. And there's a tribal community down there that now has an entire new economic benefit and resource there from all of the new types of clamming and different things that they can do now that sand and coastal area has restored, and it's really prevented a lot of erosion that was occurring on residences on one side and the tribal land on the other. So it's such a cool story about how that coastal replenishment, even over just a short period of time, can really rejuvenate those areas.
Tim and Jennifer, I have a question just in general about the Bureau of Reclamation and the dams, reservoirs that you manage. Do you deal with authorized purposes, or what does that picture look like, or what things do you have to take into consideration when you're planning sediment management?
Well, all reservoirs in the federal system are authorized by Congress, and there are in the legislation authorized purposes. I think that's the same for the Corps and Reclamation. And so if you were going to do a sediment management plan, you would have to be consistent with those project purposes, but in a lot of ways you'd be trying to preserve the functions of the dam and reservoir so they could continue to meet those project purposes.
Yeah, and it's really interesting because if you look at the original authority, I mean, it is very clear that our priority is to maintain and deliver water for the West. But over time, there's been so much increase in recreational use, endangered species concerns that need to be managed, where we kind of have a responsibility, often by biological opinions or other river restoration authority, to manage the flows differently. And that's where kind of more continuity with trying to treat the ecosystem as a big reach, so we can manage the reservoir more sustainably, both to keep that storage, but then also ideally help these downstream reaches function in a way that really supports the ecosystem and species that are threatened. So that would be kind of the ideal vision, is to balance the authority in that way so that we can better manage all of these things. And then of course we have cultural resources too, which are super important and need to be protected by the way that we operate the reservoir. Sometimes they are buried by the sediment, and sometimes they are exposed by different operations. So that's certainly something that we consider when we look at these alternatives too.
You see sedimentation in the west impacting the current drought situation, or is that two different things?
Yeah, definitely. Particularly a lot of our reservoirs that have a lot of fluctuation in stage, sediment that may have been farther up in the reservoir. Once it's drawn down, the river energy can move that sediment farther down into the reservoir, closer to the intake. So that's one thing that can really affect it. And we're experiencing just extreme amount of wildfires that are potentially elevating the sediment loads to our reservoirs due to the drought and dry conditions. So we're doing studies right now to try and understand how much those changes really impact our storage and how fast. And a lot of our smaller facilities that just have a very narrow range of active storage, are very sensitive to changes in sedimentation that can be sped up from those kind of events, particularly if you, on top of it, get these big spring rainfalls or early snow melt. So we're really trying to understand how to do that. And what we're, it's no surprise, but what we're finding is that trying to manage that sediment real time is going to be the most effective way. And the more beneficial uses we can find near the reservoir area can really help us better manage that. But it takes a lot of partnership, with different agencies, different users of the reservoir to try and navigate these complex things.
Well, and also imagine if you could start this drought with no sediment in any of the reservoirs, you'd have that much more water to be able to try and get through the drought. And so the drought is going to bring in more sediment eventually, because when you finally get the rain and snowmelt following those droughts, the vegetation is going to be quite stressed. And so sediment yield rates are going to be accelerated. So then when you go into the next drought cycle, you have even less storage to start off with.
Yeah, one other thing that Reclamation's, working on is water savings to try and balance that, but it's really difficult. So they do have a program called Water Smart that you can Google and look up. It's a pretty cool program. It has external applications and grants that are provided, for any activity that can help save water in our water budget calculations. But those are really important programs, but overall the need for the water is much greater, than the savings, but we keep trying to chip away at it.
Paul, do you want to try your audio, and do you have anything you wanted to say about the beneficial reuse research the Corps has been doing?
Yeah, how's my audio now?
Oh, so much
excellent.
better.
All right. I literally switched computers. So you've got a problem when you have 3 computers on one desk, right?
Oh goodness.
Yeah, so yes, Sandy and MSAC we worked with them a couple years ago on putting in a proposal for one of the Corps' beneficial use. I forget if it was section 1122, something like that. The Corps system was really set up through that program for existing dredging programs, places where we've already got management or ongoing dredging activities and looking for better ways to use that material. We put in proposals to that program for a number of these reservoirs and the Missouri River itself down near Council Bluffs, and we got a thanks but no thanks on those proposals because we don't have an existing dredging program at those places. So there is beneficial use going on. There's a lot of work on it, especially on the coastal areas where we're doing beach nourishment and doing better design. They're always short of sediment down there to work with, but it is a challenge here. We've got a line in this study scope that I'm kind of working on right now. What are these beneficial uses? And we've got all the likely suspects, right? You could, if not moving it downstream, you could build something with it, sell it to someone, use it in some other process, or the like. But Mark makes a great point. You're in the upper plains of the Missouri Basin, so the one thing we're not short of is sand. You know, drive a few feet and dig another hole, and you've got all of it you want in the valley there. So that's an ongoing challenge for all the management in this part of the world. So we'll continue to look for opportunities with the core programs on beneficial use, but it's the hardest question for us to answer right now. What do we do with the material if it's not all going to be or can be returned to the river? What do you do with the remainder? Yep.
Tim showed some slides about discounting. I guess, are the two agencies in communications on that? Will you be using the same type of system? Will it be like a federal system, or how does that look?
So the federal government has certain rules. I think it comes out of maybe the Office of Management and Budget, but on how economics gets accounted for in terms of discount rates. And I think the federal interest rate now is around 2.25% that they look at. That'll be changing with time. It always does. It really lags the trends that we see in the news, but I'm not really sure I'm answering your question very well, though. Are you asking if the Corps and Reclamation apply economics in a similar way?
Yeah, and I feel part of our study that we're in the middle of right now is we want to look at things in a different way with the life cycle economics. And I don't know how that discounting rate might fit into that.
Well, there are other discounting methods than the one that's traditionally used, which is exponential discounting. I think in our model that we're developing now, we've got 9 different discounting approaches to choose from. And so there's that. But one of the things are talking about in a new journal article that's about to come out is that when a lot of these projects were planned, they only looked 50 years out on the economics. And so that avoided any decommissioning cost. And also they didn't really look at how the storage was going to diminish over time. So that wasn't really considered in the economics either, nor was the surface area and how that was going to begin shrinking over time, and the impacts on recreation. That was kind of ignored. And then the downstream degradation impacts were ignored, and the upstream aggradation impacts were ignored. So they just pretty much looked at the benefits to the project as if they didn't really change. We're going to pay nothing for sediment management. And then that's how they did the economics. So part of it is discounting, but the other part is not being comprehensive enough. And a lot of economists would say, well, once you get 50 years out, we discount things so heavily that anything after 50 years doesn't really matter much. And that basically led engineers to think, well, if that's true, then we don't need to worry about, where do these projects eventually lead? What's their end of life? And what is that going to cost? What's that scheme going to be like? And how will that affect future generations? So it really wasn't looked at. And now that we're 50 years or plus, I mean, most of these projects are in the second half of their sediment design life. And in economics, you always start from today and you pretty much ignore what you've spent in the past, and you're just looking for alternatives and proceeding into the future. And now these outcomes of plugged outlet works or buried boat ramps or reduced recreation area or even reduced storage capacity, they're not that far into the future now. So when you look at the economics comprehensively, you look at all the effects, I think you start to come up with different outcomes, even with exponential discounting and even with the federal interest rates, which actually right now are, I think, some all-time lows.
Yeah, something else that I've seen that is an interesting factor is depending on the operations in the site, there may be short-term contracts and long-term contracts, and factoring in risk analysis of if the sedimentation starts to take away storage, will some of those water users look, although they are limited, look to other sources and put at risk kind of the economic return on investment and reliability of having those contracts move into the future? Will people start, leaving essentially and finding other resources? So that it's also interesting to think about the actual contractual and water user element of it.
I've got Sandy, I've got an update on some of that. In a couple of slides on the study, but what Tim is talking about, with the 9 different discount rate models and stuff, we are essentially basing our analysis in the study off of Tim and Reclamation's paper there. So we are actively trying to do that on Gavin's point right now. So I'll give a little update on that with my slides. To Jennifer's point there, it's, we'll point out a little difference here. The Missouri River Basin is the only watershed in the country where the Corps of Engineers does not charge any state or water user for the water. There's no, on other systems, states pay storage fee per unit of water for the water in the federal reservoirs. They don't on the Missouri. So as a revenue generator, once about every 10 to 15 years, somebody in Congress thinks that we should start doing that. And then that gets all squirrely for a while and then it dies down. And so, yeah, it's a little different dynamic. The revenue streams in this system are a little different than they are in some other systems. Yeah.
Interesting.
I just had a question too about kind of the historical evolution of the Missouri River system. When it started out, it was kind of a joint project between the Bureau of Reclamation and the Corps. Can you enlighten us at all on how that changed, or is there, it's probably a long time ago, but I guess, is there possibly any way of working together in the future, or is that already happening?
Paul, can you speak to that?
Well, a little bit. We won't get too deep into Pick Sloan here about Colonel Pick and the like, but yeah. So obviously we have the kind of the rapid expansion of the system is part of the Flood Control Act of 44, known as Pick Sloan, and that was a collaboration. The original idea was that the Corps wanted a lot of really big reservoirs, and the reclamation chief thought it was better to have multiple or a lot of little ones. Long story short, someone threatened if they couldn't figure it out, they were going to make a Mississippi or a Missouri Valley Authority in to mirror the TVA. Neither agency like that. So over, bourbon and cigars, it all got figured out. You have Pick Sloan essentially. But the coordination of management in the system still operates today, right? You have the Corps running the main stems and some tributary reservoirs, and then you have Reclamation has a bunch of reservoirs in the system too that they operate in coordination. There are what they call, I think it's Section 7 reservoirs that we identify by that authorization, that when certain reservoirs come in on, at certain flood pools and we're in certain flooding conditions, then the Corps of Engineers makes some of the management calls on how those tributary reservoirs are operated, so that we're integrating them into the system. When they're not in those high flood conditions and don't have an outsized impact on the overall system, then they revert to local management. So yeah, there is still coordination. on the water management side. On the reservoir sedimentation side, Tim and now Jennifer's group and a bunch of us in Omaha and other districts have been working on this together through many of the things that Tim showed at the beginning of the presentation there for going on well over a decade now between all these offices, and we continue to do so. Both Bureau and Reclamation are very active in Sedimentation Committee and the National Reservoir Sedimentation team that he talked about, and the Challenge Prize and all of that. All of that is done at a people who care level, not people who are have to care level. There is no formal document and agreement that says that Reclamation and the Corps shall do and will do this. It is a collaboration that is kind of born out of certain people with an interest and a focus on this. So we don't our collaboration doesn't fall under some specific federal authorization. It's because we share like interests and goals in reservoir management.
Well, plus it makes a lot of sense. We can do things smarter collectively than independently.
Yeah, a great example is the reservoir database information, right? We started with RSI, we built that up a few years ago. We brought Reclamation data in, so both agencies had that, and then Reclamation has had the opportunity to push that technology further for some of their specific needs, and then we're working in parallel with them. And the intent has always been that while there's two platforms with two different slightly different management goals and what they do, we've been great about cross-sharing this knowledge and the information and the data we have. So I don't think either of our products would be as good without the input from the other agencies' team members.
Completely agree with that.
Monopolize the questions. Are there any questions here or online?
Paul, I was wondering, who's the judge on the contest? Where's the judging done? And is there a set of particulars or a set of guidelines that you go by?
On the prize competition you're talking about, the judging for that?
That's the criteria.
Yeah, we've had Tim or Jennifer, correct me if I'm wrong. We've with the 3 phases, so that we're not too overly close to the content at hand. We had a set of phase 1 judges and then a different set of phase 2 judges that came in with kind of fresh eyes to evaluate that. And so the 3 of us that are on here today are it's kind of morphed into more of, we're on the steering committee for the challenge prize competition, and facilitating, getting the right judges with the right experience at the right time. And now we're moving towards, and now that we're moving into phase 3, we've got a set of judges. Have we defined the judges for phase 3, or is that reverting to some of the phase 1 and 2 judges?
It's the same as the phase 2 judges. And we're
Same as the
looking at
phase 2 judges. Okay.
criteria like, is this new technology? Is it likely to save cost? Is it likely to be more efficient? Can we get to deeper areas of the reservoirs with this new technology? Because a lot of dredging is a multi-billion-dollar a year industry worldwide, but a lot of it's focused on navigation dredging in ports and harbors and also river channels. Some relatively small fractions done on reservoirs. Reservoir dredging can be a lot deeper than the normal river dredging. And then if you're transporting, say, delta sediments past the dam, you could be going a fair distance in some of the bigger reservoirs. And so abrasion issues were something we were looking at.
Another part of that question is there any plan to implement whoever is the winner in some microcosm or some pilot plan to go ahead beyond that now that once that's chosen, once the winner's chosen?
Paul, we had heard rumor that the Corps might do something like that, but I don't know if that's true or not, or if you can
Well,
speak to it.
I guess, to be clear, it's the prize competition is not set up with a federal dredging or federal sediment removal contract at the end of it, right? There wasn't, and we did have a number of participants. That was one of the first thing they asked. They said, okay, if we get all the way to the end, do we get a federal contract, right? And no, we don't have a specific task there or award at the end of a contract. However, we are working with our headquarters right now and hope to have that, may come out in a future WRDA, but hope to more formally establish a reservoir sediment management program within the Corps so that we would have some more support from our headquarters, not just dispersed project by project, while still keeping, the decision making local, having some, some visibility at headquarters that this is going on and have some national points of contact. And the chief of engineers has asked for, ideas about near-term pilot projects, especially with this Build Back Better money that's moving around right now. So we've identified a couple of projects where we could do stuff in the very short term with some seed money that might be up to maybe a few million. We've identified a number of other areas where we need continued collaboration and to support for stakeholder engagement and what sediment management looks like. The area around Gavins is one of those. So we're hoping that maybe one or two of these technologies that come out of this would align efficiently with maybe one of these pilot projects that the chief is interested in having happen in the next year or two here. But full transparency is, we have to put that together, right? It's the onus is on our group. A lot of us in the Corps and Reclamation who work on this to connect these pieces together because nobody's going to do it for us.
I might add that MSAC has been in contact with some of the people involved with the challenge, and we're hoping to get them in cooperation to do some webinars just for our stakeholders. And we visited with Paul too about phase 3 of the study that we're in. We don't want to be limited to just what emerged from our solutions workshop last June. We want the flexibility of also possibly looking at some of those technologies closer and seeing how they might be applied at Gavin's Home.
Yep, absolutely. And, because we had a couple of things come out of the workshop last summer. And then as Sandy and we were talking, when we revisit a scoping effort for phase 3 this fall, this phase 3 of each, right? Phase 3 of the challenge, prize challenge will be done later this summer. And we'll be hopefully going into phase 3 of our sediment management plan in the fall. As part of rescoping there, it's definitely worth a look at the technologies that are coming out of this prize competition and taking a shot at developing what those technologies applied at Gavin's look like. What is the scale of those applications? And it may be, I'm pretty impressed with our econ folks and what they're doing with the current stuff on Gavin's, and I think they'd be very capable of helping us look at make an estimate on what the application of some of those new technologies might look like when the time comes.
Dr. Randall and Jennifer, one of the things that we struggle with, and Paul is well aware of this, do we build a pipeline around the dam? And our dams, when they were constructed, there was no outlet at the bottom of the reservoir, or do we retrofit the dam? What have you learned from the Far East designs of new dams and how they're dealing with this problem? Are you better to go around the dam? Are you better to go through the dam? Is there a consensus on that sort of thing?
Well, in places like Japan and Taiwan, they have a lot of rainfall. And so they're not worried about refilling the reservoir. So they're building tunnels to sluice the sediment right on through. In a lot of the Western areas, the water is just too scarce to do that. Although I'm not as familiar with the operation of Lewis and Clark Reservoir to know if you could do any sluicing or flushing. But I know in most reclamation reservoirs, that would not be an option. And so then you could look at permanently installing slurry pipelines. I mean, they'd have to be replaced and repaired at points, but you could consider having a dredge dedicated to that reservoir. And rather than a dredging program that's trying to recover decades of past sedimentation, usually that's cost prohibitive. But if you were to focus on the sediment that's coming in each year and trying to pass that downstream at a rate similar to the rate it would go downstream if the dam and reservoir had not been there, that might be economical to do something like that. And, it's not cheap, but on the other hand, eventually letting the reservoir fill up and having to be decommissioned, that's not going to be cheap either.
Yeah, it's very true. And it is challenging to route sediment through your infrastructure and ensure that it won't fail. So we do have 2 research efforts ongoing right now. Evan Lindebach is looking at abrasion resistance through the pipes that would be used to route sediment either around or through facilities to investigate what kind of techniques could be used to further their life and not have any downtime. And then Bobby Joe Merton is looking at coatings that can go on the infrastructure using different approaches if you do believe that you're going to be passing sediment through to help provide resistance and protect those features. So those are some ongoing efforts that might be of interest for some presentations at some point.
Any further questions? Thank you. It was a very informative presentation. We appreciate it and hope you have great days.